And then specifically, which things are we summing up? We're summing up those things when first j equals 0, and then when j equals 1, and then when j equals 2. This tells us the first value of j to start at, and then where to stop. So this is j equals 1. We evaluate this thing, we get, 0. J equals 0. We evaluate this thing, we get 0. Then j equals 1. We evaluate this thing, we get 5. And then j equals 2. We evaluate and we get 10. And then the big, scary-looking symbol there is just, all it is just means sum. Sum up all those things. So 0 plus 5 plus 10 plus 15. Okay, so then let's look at that. While we're on this topic, let's look at the last one in the homework. So this is 4.7, right? So this one right here. So what's going on with this one? So in all these other ones, you can pick off the pattern that emerges from one to the next, but this one's kind of weird. 1, 3, 4, 9, 16, 15. What's happening here? So you can best see it kind of towards the end here. So 16, then 15, then 64, then 21, then 256, then 27. What you should start to see there is there's really two patterns, and they're alternating. That's, if you study that long enough, you should see that this seems to be a pattern. And then this seems to be its own separate pattern. Okay, so what can we do? It's a sum. So what property of sum do we have that could make this would be really helpful for us? Yeah.
So you can separate the two different sums.
Okay.
Sums and have them back together.
And why can you do that? So why can we do that? Yeah. So yeah, cumulative. What is the word?
Cumulative.
Cumulative?
Yeah.
And what is that the right word? Commutative. That's the word. So what does you know what commutative means? Yeah.
You can do it in any order.
Any order you want, right? So you can add together values in any order that you want. So we're going to pick all the ones that I've underlined in blue and group those together, and all the ones in red and group those together, and then add up all the blue ones first, and then add up all the red ones after that. We can change the order with addition. We get the same result. So for the red, what pattern do we have there? So we know we're summing up. We got 3, 9, 15, 21, 27. And what's happening each time? We're adding 6, right? We're adding 6. So what formula can we have for that?
6k plus 3.
Okay, so when n equals 0, we have 3, and then every time we add and up to, no, not infinity, because it stops right there. So what is n there? Well, we could do 3 plus 6n equals 51, and we could work backwards to get what n is. I think, is it 16? 8? 8. Yeah, right, okay. So this will give us all those red values added together, and then the blue ones, what do we have there?
Double each value starting from 1 in the square.
So these are all what? Powers of 4, right? 4 to the first, 4 to the second, 4 cubed, 4 to the fourth, and that could be seen as 4 to the 0, so we can just do 4 to the n. And then what is this? Is that also the 8th? Is that the 8th power of 4? Should make sure. What is 4 to the 8th? Got GC here.
Yeah, it's 4 to the 8th.
So you need to put parentheses around each one. I hope this is right. So it took that second sum and it made it in the part of the term of the first sum. So by putting parentheses around each one, we got it. Okay, questions on summation notation. So we'll see. That's going to come back in a week or two. We're gonna need that again. Yeah.
Question. So I did the second one a little bit differently because I didn't quite see this power before initially.
Right.
What I did is I took the last term and divided by 2, the power of 2 times k.
Okay. Yeah, there could be different ways to do it.
It adds up.
Yep, if we add up the same thing. Yep. Okay, so let's look at the talk about the Usain sheet that you did. Is there any questions? So your homework that you had for this. I had all this stuff changed and then I didn't save and it crashed. Sorry. So let's do it again here. Okay, so you started off with this, and what was this graph? This was the time since you started running as our independent variable, and distance from the starting line as the independent or the dependent variable on the y-axis. And we went through and we said we want to find some different rates of change at different moments, right? Rates of change at different moments. So we could look at, let's do one that we didn't do. So how about at 6.6? All right, so at 6.6 seconds after he started running, how could we find his speed or the rate of change of distance from the start? What kind of approach did we take to figure out what his speed was or his rate of change at this moment? Somebody knew. Yes, sir?
Use a tiny change in x to calculate.
Right, right. So we said if we look at a moment, which is a very small change, zoom in here at a moment at 6.6. Do it again. And the graph becomes apparently or seemingly linear for a small enough amount of time so that we can consider that we have constant rate of change for that very small amount of time because the graph is essentially linear for the moment. And then we calculated what? What did we calculate? Where's Michaela? Michaela Sanchez. Where are you? What did we? So now we want to find the rate of change at this moment, 6.6 seconds. What do we do? Okay, so the change in x here, I think I'm showing a change in x here of 0.015. 0.01005. Okay, and you said? Find the corresponding change in y. And then what? Right. And so whatever that turns out to be. So I have that in here. So that turned out to be 12.395 according to... And what would the units on that be? What would the units on the 12.395 be? Meters per second. And we said the meaning of that value is, how are we doing on this? Where's Justin Horn? Yeah, so can you
That's
articulate?
the
It's the constant rate of change in our moment, and what does that mean? The constant rate of change of 12.395 meters per second.
So at any point in our moment, the distance traveled from the start is our meters times or seconds times.
Okay, yeah, so you're on the right track. Yeah, you got the right idea. How about, where's Mark M? Mark, yeah. 12.395 meters per second. What? Right, it's the constant rate of change. And what does that number mean? 12.395 meters per second. Is that a hand back there? Tell me. Okay. Trailed off. Yes, sir. For any change in seconds, he runs 12.395 meters. For any change in seconds, he runs 12.395 meters. Agree with that? Yeah, go ahead. Right. For any change in time, the corresponding change in distance is 12.395 times as much as that change in time. Now, but we have a qualification now. It has to be a small change in our moment, right? It has to be a small change in our moment, okay? So, if you haven't gotten that yet, meaning of a constant rate of change, we've got to get it now. We've got to get it now. It's really important. We've worked on it a lot, but it still seems like there's a good portion of you that still are kind of grasping that. The meaning of a constant rate is, given a change in the independent variable, the change in the dependent variable is in this case, 12.395 times as much as that change in the independent. That would be our change in time, okay? But now this only holds true for a very small change in x within a moment, okay? So make sure that we're getting that, okay? Yeah?
In this particular instance, it would be saying that he's running this many meters per second.
Right, but we want to know exactly what that means, because this is way less than a whole second, right? It's way less than a whole second. It doesn't really make sense to talk about 12.395 meters, because this is way shorter than a second. This is like a really small fraction of a second that we're looking at. So that's why this works, right? This is our most comprehensive way to think about constant rate of change. Okay, so you did this lots of times, right? You did it lots of times, and you made a table. And then from that table, you should have made a graph like this. Is this kind of what your graph looked like? Yeah. Okay, you should have made it. You should have plotted points where the independent variable was still the time to start, but the dependent variable was now rate of change in meters per second. So we got to know what we're looking at here. So now it's 6.6 seconds on this graph. 6.6 seconds on this graph. How can I know how fast he's running or what his rate of change is at 6.6 seconds using this graph? I come up here and I zoom in and I do dy over dx, right? You're shaking your head. I want to know how fast he's running at 6.6 seconds. Tell me. Yeah, the rate of change. Rate of change. It's right. He said it's the y value, right? So this is a rate of change function. And if it's a rate of change function, where do we see rate of change? How does rate of change come out in a rate of change function? As the y value of any given value of independence. So this ordered pair is what? 6.6 and 12.395. The y value is the rate of change in a rate of change function. There's no zooming in. There's no finding dx, dy, because this dependent variable is telling you what the rate of change is. Okay, does it make sense? All right, so this is, we want to practice this a little bit. Production example. So you're going to work on the side that has 3 graphs. Work on the side that has 3 empty graphs. So the rate of change is steady at 1.5. That means at 1 minute the rate of change is 1.5. At 6 minutes the rate of change is 1.5. Okay, so I think most of you have completed the sheet, talked about it, thought about it. Let's go over that. So these should all say minutes. So your sheet is right. This is minutes. On the x-axis is number of minutes since the faucet was turned on. Okay. So rate of change. The rate of change, what? It's constant. It's 1.5 gallons per minute. Is that right? 1.5 gallons per minute. And so what is the rate of change at 3 minutes? 1.5. So we have the point on that graph. What's that point? 3, comma, 1.5. And after a half a minute, what's the rate of change? 1.5. So the y value on the rate of change graph is the rate of change, right? So at 0.5 minutes, 1.5. And so if the y value, if the rate of change stays at 1.5 gallons per minute, then the rate of change graph is going to stay, its y value is going to stay at 1.5 gallons per minute for any amount of time that's gone by. So all your correspondence points lay on this horizontal line, right? Form this horizontal line. So contrast that with this. We said at what? At 6.6, this is Usain, at 6.6 seconds, we said his rate of change was 12.95, was that right? 395? So at 7 seconds, is his rate of change 12.395? Is it more or less? So the rate of change is going, this rate of change is a changing rate, right? So when he runs at a changing rate. So at 7 seconds, it's no longer 12.395. It's something else. So we say, was it R sub f? Is that what we called it? So we could write that ordered pair this way, 7, and then use function notation for our function that's called R sub f of 7. But R sub f of 7 is something slightly greater. It's a higher rate of change than at 6.6. So that rate of change here in his graph is a changing rate, right? It's a changing rate. And given any number of seconds since he started running, the correspondence point, the y value tells you the corresponding rate of change. Back here at 1 second. This point is 1 comma r sub f of 1. And that's a lower rate than these other two. Right? And where do we see, how do we know what that is? It's whatever this y value is. So that y value, can you stop kicking the desk? Can you stop kicking the desk? Thanks. So right here is the y value for when x is 1, and that's the rate of change corresponding to the time 1 second after. Okay, going back to this. Okay, so what about the number of gallons added to the tub? The number of gallons added to the tub at time equals 0, how much additional has been added in? 0, right? 0, and then every minute there's 1.5 more gallons than there was before, because that's our rate of change, right? So that's what this one looks like. Number of gallons added, it starts at 0, okay? And then number of gallons in the tub has the same kind of profile of how the gallons goes up, but at time equals 0, we have that initial number of gallons too. Okay, so here's 3 different types of graphs. We have a really simple situation here with 3 different types of functions that are going to be really important for us to be able to keep track of when we get in these different situations. Okay, and this first one is a rate of change function, right? It tracks the rate at which a quantity changes. Y values of a rate of change function are the rate of change. The y values are the rate of change. Okay? And then this one we're going to call the net accumulation function. Net accumulation. This tracks the amount of change, right? So starting from 0, how much did the quantity change? And that's the same, what we're saying here, number of gallons added. That's how much the gallons changed since we turned on the faucet. And then this last one we're going to call the total accumulation function. The total accumulation function. That tracks the total accumulation of a quantity, including what you had to start with, right? What you had to start with. Okay, so these terms are going to be really important when we have these different functions. Rate of change function, a net accumulation function, which tracks the amount of change, and then a total accumulation function, which gives us the total accumulation of the quantity at any value of the independent variable, which will include some starting value, if you have a starting value. So we want to have our terminology straight, but also our understanding of what these different kinds of functions are. So we start with this really simple example with the tub to really pinpoint the differences or what these 3 functions mean and the terminology we'll use to describe them. Okay, any questions on that? Okay, so on the first day, and you read in the preface here, we said that calculus is really about 2 goals. You know how much of something you have, and you want to know how fast it's changing. You know how fast something is changing, and you want to know how much of it you have. So now we've gotten all the building blocks, laid all the foundation, and we're going to begin with endeavor B. We're going to begin with endeavor B, which says, you know how fast something is changing, you want to know how much of it have. So this phrase, you know how fast something is changing. How would you know? What would you have that would tell you how fast something is changing? Rate of change function, right? This is describing some rate of change function for some quantity. So based on that rate of change function for that quantity, we want to build what?
Total accumulation function.
Or both, either one of these. So given the rate of change function, you know how fast something is changing. You want to know how much of it you have. Well, so that could be net accumulation is a version of that, how much you have, but also total accumulation. That's also a version of how much you have. Both of these are kind of two different perspectives on how much you have, right? how much it's changed, and then how much actually you have. Okay? How much accumulation you've had. So this is where we're going in the next 2-3 weeks. And this is when it gets hard. This is when it starts getting hard. Okay? And that's why all these things we've done in the first month are critically important. They're all going to be involved in this process of, we know how fast it's changing, we want to know how much we have. Okay, so let's just glance at this on the back. So save this sheet. We'll use this sheet Friday and maybe Monday, so don't throw this away, bring it to class Friday. But here is this function, gives the rate of change of volume of oil expelled per day by an oil rig that begins leaking at t equals 0 days. So this is a rate of change function. This is a rate of change function. So can you imagine a function b that gives the total amount of oil expelled x days after the rig started to leak? So here, the net accumulation and the total accumulation are the same because there was no leaked oil to start with. Okay, does that make sense? So that net accumulation and your total accumulation, same graph or same function. So can you imagine what that function looks like? So we're starting from at 0 days, 0 oil was leaked, and then this tells us the rate at which the oil started leaking. Can we come up with just a rough sketch of the function that would tell us how much oil had leaked at any given time? So give it a shot. Give it a shot. So if this is the rate of change, then what would the net accumulation of oil look like? Which would be the same as the total accumulation of oil for this context. What would that look like? So we're just trying to come up with a rough sketch. No numbers, no calculations. So we didn't have much time to do it, but starting at 0, what? The rate is the highest at first. So the amount of oil that's spilling out is shooting up the fastest, but then that rate slows down. That rate slows down. And so then the oil expelling into the ocean is at a lower rate. So it's not shooting up as fast, right? Not shooting up as fast, and then increases its rate at the end. So something like this. So what is our goal? Our goal is, given this rate function, we want to know this function exactly, not just a rough sketch. What is this v function exactly, given that rate function? Okay, and so this is starting our 2 or 3 week journey of figuring that out. Okay, so you know how fast a quantity is changing. You want to know how much of it you have. That's where we're going.